The purpose of this lecture is to investigate the global minimum of the RSS function, the residual sum of squares, for a linear trend line when we have data on an x variable and a y variable. So the setup, we have a sample of n observations, we have data on the x variable and the y variable, and we identify a linear trend line whose equation is y is equal to b1 plus b2x. And from this trend line, we form residuals and the residual sum of squares. So we're going to denote RSS by this function f. And it depends on these two variables, b1 and b2, which are the intercept and the slope. So this is the function. And then, according to the least squares principle, we want to find the values of b1 and b2 that minimizes this function. We have seen in another lecture that this function has precisely one stationary point. The stationary point being the solution to these two equations, df db1 equal to 0 and df db2 equal to 0. We have seen that this solution to this system of equations is b2 is sum xi minus x bar yi minus y bar over sum xi minus x bar squared, and b1 is y bar minus b2 x bar. So that is the only stationary point. That, of course, does not prove that this point is a global minimum of the f function. However, we have the following result. If f is a convex function on a domain A and x is a point in A0, where A0 is the interior of A, and x is a stationary point, then this value of x will be a minimum point of f. In our case, the domain is all of the Cartesian coordinate system R2. So our stationary point here is indeed an interior point. So if we can show that f is convex, then this will be a minimum of the function f. This will be a minimum point. You can also go beyond that. If f is strictly convex, then this x value is the unique minimum point. It will be the unique global minimum point of this function f. So what we're going to show now is that this f function is indeed, well, actually, I'm going to show that it's strictly convex. Then it will follow that this stationary point that we have found is a global minimum of the RSS function. In order to show that f is strictly convex, we use the following result. If the Hessian of the function is positive definite for all x and y, well, this is a generic result. Our variables are called b1 and b2. Then f is strictly convex. So we are going to find the Hessian. That's the matrix consisting of the second partial derivatives, and we're going to show that it's positive definite. Remember, the Hessian for a function of two variables is defined as this 2 by 2 matrix, where you have the second partial derivative with respect to the first variable twice, then the second with respect to the first and the second. This one is with respect to the second and the first, but that's going to be the same. b1, b2 should be a 1 there, and then the second partial derivative with respect to b2 2 times. So we need to find these three second partial derivatives. We already know that the f, the b1, and now we need the entire expression, not the one where we divided away -2. So that's -2 times summation yi minus b1 minus b2 xi, and the partial with respect to b2 is -2 summation xi yi minus b1 b2 xi. So let's do the second partial with respect to b1 twice. So define the second order derivative of f with respect to b1 twice. All I need to do is differentiate this guy with respect to b1. I can move it, the derivative, inside the sum as before. So I'll write it as -2 times the b1 of this expression. And that's pretty straightforward. If I differentiate with respect to this one, I'll just get a 0. Here I'm going to get a -1, and here a 0. So the whole thing is -2 times summation of -1. And there are n terms in this sum. So it's -2 times n times -1, which is 2n. To find the cross partial derivative, I can either differentiate this first one with respect to b1, or this first one with respect to b2, this one with respect to b2, or this one with respect to b1. I will get the same result. So let's do the derivative of the first one with respect to b2. So it's -2 summation d db2 yi minus b1 minus b2 xi. I get 0 from this, 0 from this. I get minus xi from this. So it's -2 times summation minus xi, or 2 times summation xi, and that's the same thing as 2 times n times x bar. So we have one more, and that's the second with respect to b2. And then I do the derivative of this with respect to b2. -2 summation the b2 of this expression here, and let's put the xi inside. So d db2 of xi yi minus b1 xi minus b2 xi squared. With respect to this one, I get 0, and with respect to this one, I get minus xi squared. So the whole thing is -2 times summation minus xi squared, which is 2 times summation xi squared. So let's plug it in. We get the Hessian, which is 2n x bar, 2n x bar, and 2 times summation xi squared. So what we need to do now is to check that this is positive definite. The rule for a 2 by 2 matrix for being positive definite is as follows. This one, and again xx refers generically to the first variable. Our first variable is b1, so this is the second partial derivative with respect to the first variable twice. That's this guy. that must be strictly positive, and clearly it is, and it's strictly positive, so that's an OK. And second, the determinant of A must be strictly positive. So let's find the determinant of H. So the way I remember it is, think about it in terms of this symbol here. So you do 2 times n, that's the first element. You multiply that by this element, so times 2 times summation xi squared. Then you do a minus sign, and you move on to this element, 2n x bar, and then you go to this element, 2n x bar. And that's equal to 4n summation xi squared minus 4n square x bar square. We can take out 4n, and then it says summation xi squared, and then we are left with n x bar square. And this expression, we used this before, you can write that as summation xi minus x bar square. So the whole thing is 4 times n times summation xi minus x bar square. If we look at this expression, we have a 4 which is positive, we have an n which must be strictly positive, and we have a sum of squares. Well, the terms inside the sum can never be negative because they're squared. So this sum must always be greater than or equal to 0. However, we have ruled out the possibility that it's equal to 0, because if this is equal to 0, the OLS formula fails, because remember, B2 has as its denominator summation xi minus x bar square. So this cannot be 0, because then we can't calculate B2. So this must be strictly greater than 0, and the whole thing is strictly greater than 0, which is precisely what we need. So that means that our Hessian is indeed positive definite for all possible values of B1 and B2. And this finally then proves that this stationary point is the global minimum point of RSS.